When Tartaglia was only 14 years old, he fell into the abyss and met Skirk. She trained him for 3 months, however when he came back to Teyvat, only 3 days had passed. Initially this sounds weird, but in Special Relativity, objects in motion experience time slower, so it's possible for this to happen. If Teyvat is moving with respect to the abyss, then time on Teyvat will tick slower than in the abyss. But something strange happens when you consider the other perspective. On Teyvat, the abyss would appear to be moving at the same speed but in the opposite direction, meaning that the abyss's time should also be slower. If both see each other with slower time, then how can 3 months pass in the abyss but only 3 days elapses on Teyvat? Hello, Count Sacke here, back with another Genshin Impact video. Today, I'll be explaining how Tartaglia's experience is completely possible with physics developed by Einstein, and how it relates to one of the most famous paradoxes in physics. If that sounds interesting to you, be sure to subscribe so that you don't miss out on future uploads about math, physics, and engineering related to Genshin. You can also like, share, comment, or leave a super thanks on the video to help me out in the YouTube algorithm. Thank you to everyone who participated in the video topic poll for making this video possible. Lastly, I would like to explicitly thank Eternal Dongo Work for becoming my first ever channel member. Channel members get access to behind the scenes footage or even exclusive videos, so if you're interested, feel free to check it out. It's been a bit since our last video, so I think it's best to have a small recap of Special Relativity. Special relativity is a theory of physics about how time, space, and motion is affected by different points of views called reference frames. It has 2 main postulates. One is that the laws of physics for all inertial reference frames are the same, and 2, the speed of light in a vacuum is constant for all reference frames. As a consequence of a constant speed of light, when someone observes another reference frame moving, they will see that the moving frame experiences time at a slower rate and that lengths become shorter in the direction they're moving. These real-world phenomena are called time dilation and length contraction respectively. Today, we're only focusing on time dilation as length contraction isn't necessary to understand Childe's scenario. The equation for time dilation can be determined with the following. Tb with respect to A is equal to gamma times Tb with respect to B. Gamma is what is known as the Lorentz factor and has a value that ranges from 1 to infinity. One new variable I want to introduce is this beta term. It's defined as the ratio of an object's speed to the speed of light. This is useful because for time dilation and length contraction to be significant, objects need to have very high speeds, so the exact values can be very large. In the time dilation equation, Tb with respect to B is B's proper time. Tb with respect to A, on the other hand, is called the coordinate time and is technically measured in terms of A's proper time. But know that it's not B's proper time. Proper time is the elapsed time for an observer in their own reference frame. It's the actual amount of time that an entity experiences, so you can imagine that everyone has their own clock, all ticking at different rates depending on circumstances. Coordinate time is basically the proper time of the reference frame you measure things from. An alternative way to measure proper time is by using the spacetime interval. This quantity is analogous to the quote-unquote length of an object through spacetime, and it has this equation. Keep in mind that this uses Einstein notation, so both the mu and nu indices are summed over from 0 to 3 because we have 1 dimension of time and 3 dimensions of space. Since we're dealing with flat spacetime, the metric tensor is equal to the Minkowski metric, which has this form when using Cartesian coordinates. This allows us to calculate the spacetime interval. The spacetime interval is the spacetime interval between the point of view of the observer and the point of view of the entity. The spacetime interval is the spacetime interval between the point of view of the observer and the point of view of the entity. The spacetime interval is the spacetime interval between the point of view of the observer and the point of view of the entity. The spacetime interval is the spacetime interval between the point of view of the observer and the point of view of the entity. The spacetime interval is the spacetime interval between the point of view of the observer and the point of view of the entity. The spacetime interval is the spacetime interval between the point of view of the observer and the point of view of the entity. The spacetime interval is the spacetime interval between the point of view of the observer and the point of view of the entity. The spacetime interval is the spacetime interval between the point of view of the observer and the point of view of the entity. The spacetime interval is the spacetime interval between the point of view of the observer and the point of view of the entity. The spacet From here on out, I'll be going forward assuming you know the concepts behind proper time, spacetime intervals, and how to read spacetime diagrams. If that sounds like gibberish to you, I highly recommend that you pause this one and watch my video, Relativity and Time Dilation in Genshin Impact, for a more in-depth explanation of these topics. Whether or not you've learned relativity, you've most likely heard about the twin paradox. Understanding this is key to figuring out how Childe's experience is possible, so be sure to pay attention. To start the discussion, let me tell you a short story. Aether and Lumine are traveling the cosmos but decide to take a stop on a planet. During their stay, Aether sees a distant star and says he wants to take a detour for some quick sightseeing. However, Lumine says she's tired and wants to continue resting on the planet. After arguing for a bit, the two agree that Aether can go alone, but he has to come back in 2 days. To make sure that Aether comes back on time, both of them bring a stopwatch and start them at the same time. Aether gets on the spaceship and heads to the star. It takes him 1 day to reach it, but once he gets there, he turns around and goes back to the planet, which takes him another day. When he arrives, Aether greets Lumine, but sees she's upset. She asks, "What took you so long?" Aether replies, "Huh? What do you mean?" She shakes her head and shows her clock saying, "Don't act dumb, it's been 3 days." Aether is surprised to hear this and says, "No, I was only out for 2 days." The siblings continue to argue for a while, but eventually they make up and continue exploring other worlds. So, why is it that Aether spent 2 days on his round trip, but Lumine said she was waiting for 3? Well, the answer is that from Lumine's point of view, Aether got on the spaceship and flew to the star and back at high speeds. Because Aether was moving relative to Lumine, she would see that he has dilated time, hence why her proper time became larger than his. We can make use of the time dilation equation to determine Aether's speed. There are 2 segments Lumine needs to consider: when Aether is going towards the star, which I'll label as A1, and on his return trip back to the planet, A2. Overall, the total time of Aether's round trip, TA with respect to L, is equal to the sum of the 2 times, TA1 with respect to L plus TA2 with respect to L. Because Aether's speed is the same throughout the whole trip, TA1 with respect to L is equal to TA2 with respect to L. From here, we can make use of the time dilation equation and then solve for beta of A with respect to L. Knowing that tau A is equal to 2 days and tau L is equal to 3 days, we can now calculate Aether's speed. Here we see that if he moves at approximately 74.536% the speed of light, 3 days will pass for Lumine, but only 2 days will pass for Aether. Paradox solved. Easy, right? But hold on. What if we considered Aether's point of view? When we're in his perspective, Lumine is the one who's moving at 74.5% the speed of light, but in the opposite direction. This means that Aether should see Lumine's time dilate, and she should have a shorter proper time than his. Making use of the time dilation equation, we find that 2 days, or 48 hours from Aether's POV, only translates to 32 hours for Lumine. Where did the extra 40 hours come from? Somehow Lumine would observe that Aether would have less proper time, but Aether also observes Lumine with less proper time. Personally, for the longest time, I wasn't able to figure out the solution to this one, and to be honest, it's perfectly reasonable to be confused as this is a very difficult thing to grasp. To solve the paradox, we need to talk about non-inertial reference frames. There's a very specific wording to the postulates of special relativity. If you're diligent, you might have noticed the term inertial, which means that the reference frame isn't accelerating. It's easy to forget, but we're all living on one giant non-inertial reference frame. The Earth spins on its axis, and this gives rise to strange effects, such as the centrifugal and Coriolis force. Near the equator, you'll actually weigh less because the centrifugal force is stronger there. And if you're trying to snipe a target directly upward or downward along your line of latitude, you'll need to aim to the side, even if there isn't any wind. These effects are only noticeable on large scales due to how weak they are, but there's actually one that we can all see: gravity itself. The actual explanation behind why this is true is best suited for another video. In fact, I actually plan on discussing this in my next relativity video, where I talk more about the equivalence principle, so again, be sure to subscribe so that you don't miss out on that one. Whenever you're in a non-inertial reference frame, you need to make sure to account for something called inertial forces. The Coriolis force and the centrifugal force are examples of inertial forces. For example, if O is an inertial reference frame observing an accelerating frame A, Newton's second law is the typical sum of forces of A is equal to the mass times the acceleration of A. However, if O is accelerating, it becomes this giant expression. As you can clearly see, it's a lot more complicated. Luckily for us, we won't be talking about this today. What's particularly strange of inertial forces is that they're only visible when you're within the accelerating frame. Consider this example with Aino and Inefa riding on a carousel that's spinning counterclockwise as shown. Meanwhile, Paimon is stationary on the ground because she fell off. Aino wants to play catch with Inefa, so she throws a ball directly towards her. From Aino and Inefa's point of view, they will see the ball curve away. By Newton's first law of motion, objects without forces acting on them should maintain a constant momentum. However, objects whose momentum is constant travel in straight lines. I've shown this in my video, What Was Alhaitham Reading? Because the motion is curved, the ball's momentum isn't conserved. So, Aino and Inefa must say that there's some sort of force acting on the ball. To be more specific, this is actually the Coriolis force. However, if you were to view this from the perspective of Paimon, the ball moves in a straight line, so its momentum appears to be conserved. Because of this, Paimon must conclude that there wouldn't be any forces acting on it. There really is something odd about the force that Aino and Inefa see. From their point of view, this mysterious force appears to have no source and affects the entire universe simultaneously. To emphasize this, there could be a tiny pebble 10 quintillion light years away, and the inertial forces would still act on it instantly. Due to how crazy this sounds, Aino and Inefa must conclude that they are the ones who are accelerating and not the rest of the universe. Sure enough, simply by changing your perspective to Paimon's point of view, the inertial force doesn't appear to exist. There's this idea that because inertial forces are only a result of being in a reference frame that's accelerating, they're quote-unquote fake or quote-unquote not real. Despite this, inertial forces do have genuine effects, as I've mentioned earlier, and if you don't account for them, you will not get the right calculations, so you need to include them. You may believe yourself to be an inertial reference frame because you don't have relative motion with respect to your immediate surroundings, but such observations can be misleading. Sometimes they can just be very small, and that you can only notice them on the scale of the Earth, but they are nonetheless there. If you want more references on the Coriolis force specifically, you can watch these two videos, one from What the Physics, and the other from Atlas Pro. For more detail on inertial forces in general and how they affect us, I highly recommend this very underrated video by OV Astronomy called The Reality of Fictitious Forces. Anyway, before we head back to the twin paradox, we need to talk about a misconception about time dilation. That is, the misconception that objects in motion will always appear to have slower clocks. Consider the following scenario. Aino needs help, so she calls out to Inefa by sending periodic signals to her. Aino is stationary and emits a flash of light every tau a amount of time, while Inefa moves towards her with a velocity vi with respect to a. At a distance of xi1 away from Aino, the light beam reaches Inefa. Notice that because she's moving towards her, the light beams reach Inefa faster than tau a. Let's call the time that it takes for the next light beam to reach Inefa ti with respect to a. What we want to do is to figure out the time between flashes in Inefa's perspective, so we need to calculate tau I. First, let's write out what we know. Because the light is emitted every tau a amount of seconds, this means that they will be equally spaced. We'll let this space be equal to L, and it has this equation. L is equal to c times tau a. Next, if we denote x equals 0 to be at Aino's position, and the right as the positive direction, we can figure out the initial positions. Inefa's initial position xi1 is simply at positive x0 plus L, and the light beam's xc1 is at x0. From here, we need to make use of kinematics to describe the equations of motion for the light beam and Inefa. Since this is just constant velocity, things are quite simple. The only thing to note is that because Inefa is traveling to the left, VIA would be negative since the right is positive. From here we should recognize that at the moment the light reaches B, they have the same exact positions, so xi2 must be equal to xc2. Lastly, we want to see things in terms of Inefa's proper time, so all we need to do is to make use of the Lorentz factor. In the end, we get this equation. Tau a is equal to tau I times the square root of 1 plus beta I with respect to a divided by 1 minus beta I with respect to a. Let's make some observations. All objects with mass must move at speeds less than the speed of light, so this implies the following inequality. 0 is less than or equal to beta I with respect to A, which is less than 1. 1 plus beta is always greater than 1 minus beta, so the term inside the square root is greater than 1. Lastly, the square root of a number greater than 1 is also always greater than 1. We can directly see that from Inefa's perspective, the time that elapses for Ino is faster than hers. Overall, for an object moving towards another reference frame, that object will actually observe that the other frame's time speeds up. If you repeated the derivation but for when Inefa is moving away from Ino, then she will see Ino's time slow down. This proves that it's possible for an object to be in motion and it will actually appear to have faster time. These effects where time slows down because you're moving away or towards an object is actually called the relativistic Doppler effect. And, well, it is actually related to the same exact thing as the Doppler effect that you might know. The common example given is when an ambulance is going towards you and then past you. While it's going towards you, it sounds high-pitched, but when it's going away from you, it sounds lower-pitched. This is the same exact thing, but instead with light waves. Currently, we've only assumed that the velocity of the objects remains constant. However, we also need to account for acceleration. Unfortunately, I couldn't figure out a simple way to derive this without going on a long tangent about Rindler coordinates. The simple one I could find was from this video by Faculty of Con called How Gravity Alters Time and Frequency, Gravitational Redshift, and Time Dilation. He explains it pretty well, so I recommend that you watch it. In any case, the time dilation due to constant acceleration is given by the following expression. Tau a is equal to tau I times e raised to plus or minus al over c squared. If the exponent is positive, then that means that I must be accelerating towards A. However, if it's negative, I must be accelerating away from A. In this equation, A is what is known as the proper acceleration of I. You can think of this as being the acceleration an object actually experiences and what they would measure using an accelerometer. Let's focus on the case where I is accelerating towards A. So the exponent must be positive. If I has a proper acceleration of A while at a distance of L from A, the proper time of A ticks at a rate faster than I. Let's go back to the twin paradox and figure out what's happening. Earlier, we established from Aether's point of view, he calculates that only 32 hours should pass for Lumine because he sees her moving at about 74.5% the speed of light. While this is true, it's missing one very important detail. After Aether reaches the star a day later, he needs to turn around to get back to the planet. Acceleration is the change in velocity, and they are both vector quantities, meaning they have both a direction and a magnitude. While the magnitude of Aether's velocity is constant, his direction changes, which therefore means that Aether accelerated. We actually need to account for the passage of Lumine's time while Aether is accelerating, so recall the equation for time dilation of an accelerating frame. Because Aether is accelerating towards Lumine, we use the positive exponential. Next, what I'll do is make use of the Taylor series for e to the x around x equals 0, then neglect higher order terms. This leaves us with an approximation of the formula, but don't worry, it'll give surprisingly accurate results, as we'll see shortly. Recall from the kinematic equations that the change in velocity is equal to acceleration times time. This implies that the proper acceleration will be equal to delta VA divided by tau prime of A. For delta V of A, it's going to be the velocity of Aether on his return trip minus the velocity of his outbound trip. The other kinematic equation we need to remember is that distance is equal to velocity times time, so L is equal to VA with respect to L times tau L1. Recall that tau L1 is equal to Lumine's proper time from the moment Aether departs to the moment he gets to the star. We can then substitute these quantities back into the equation. From here, recognize that the time Aether spends accelerating is very small in comparison to the duration of the whole trip, so tau A prime can essentially be set to 0. And if you want the change in direction to be instantaneous, you take a limit as tau A prime approaches 0. We can then substitute the respective values into the equation to calculate Lumine's elapsed proper time during the turnaround point from Aether's point of view. Here we can see that we managed to find the missing proper time of 40 hours. Hopefully you can now see that because Aether accelerates towards Lumine, he actually sees her time speed up. In fact, it has been experimentally proven in real life that this is true. The reference frame that accelerates will be the one that ages less. Now, I want to present an alternative solution to the twin paradox using spacetime diagrams and the spacetime interval. From Lumine's point of view, she stands still, so her path through spacetime is simply a vertical line. Knowing Aether's path allows us to calculate his spacetime interval, which can then be used to determine his proper time in terms of the amount of proper time that elapses for Lumine. As can be seen on the spacetime diagram, there are two different paths to integrate along, A1 and A2. However, because beta for both A1 and A2 are the same, this simplifies the expression. Because Aether will also measure the same spacetime interval, this means that S is also equal to C times tau A. As you can see, using the spacetime interval also gives us the correct answer as we should expect. But how does Aether's spacetime diagram look like? Aether, relative to himself, will always see himself as the stationary one, so his diagram should look like this. But in this spacetime diagram, Lumine looks like she's the one who accelerated, and thus would have a smaller proper time than Aether, which gives rise to the paradox again. Okay, I have to admit, I'm being dishonest here because I animated the transformation from Lumine to Aether's perspective incorrectly on purpose. Let me do it correctly this time. Wait a second, Aether's trajectory doesn't fully straighten out. In fact, from the perspective of his outbound trip, he would see that his return trip is at 95.8% the speed of light. I'll flash on screen my calculation for this. It's okay to be a bit skeptical here because Aether keeps his speed constant, so what gives? While Aether's speed is constant, that is only considering the magnitude of Aether's velocity and disregards his direction. From Lumine's point of view, his initial velocity is 74.5% the speed of light towards the right, but his return trip is the same speed, but towards the left. These are very different paths through space-time, and Aether must say that either he or Lumine has accelerated. The reason why Aether can conclude he is the one who turned around is because he observes an inertial force field that acts instantly across the entire universe. Due to the absurdity of this inertial force, Aether knows that the reason the force field arises is simply due to him being within an accelerating frame. Lumine, on the other hand, if she carried an accelerometer, she would not measure any force whatsoever, so she cannot be the one who turned around. I mean, technically her accelerometer would read the value of gravity for the planet, but the important thing is that the value is less than Aether's, and well, we're neglecting gravity in this example for simplicity. From here, you could calculate Aether's spacetime interval for his entire trip, which will give the same results that we would expect. And there we have it. The paradox is solved. From all perspectives, Aether will experience 2 days of elapsed time for his trip, while Lumine waits 3 days. From Lumine's point of view, she would see Aether moving such that his time dilates, causing only 2 days to elapse for him. From Aether's point of view, however, he sees that 16 hours passes for Lumine on his outbound trip, then at the moment he turns around, he sees that 40 hours passes for Lumine. And on his return trip, another 16 hours passes for Lumine, amounting to a total of 72 hours or 3 days. Before we continue, I would like to mention that there are some who claim that there's still a paradox and will dispute the solution I've provided. In my problem, I've already assumed that Lumine is inertial, but it's a lot harder when you don't know beforehand. The point of contention mainly lies in whether or not acceleration is absolute or relative, and whether or not you're able to detect it in the first place. If acceleration is absolute, then it's possible for Aether to know he accelerated due to the inertial force field. If acceleration is relative, however, then this is where problems arise. Currently though, the common consensus is that position and velocity are relative, while acceleration is absolute. However, the nuances of this discussion isn't very relevant to this video, so if you'd like to learn more about it, feel free to look around. It's also worth mentioning that there are a lot of different twin paradox scenarios that people have come up with. If you want to hear more about these different cases, I highly recommend this video by Kuvina Saidaki. In addition, the channel Physics, Problems and Solutions has several videos about the twin paradox that I can also recommend. Alright, let's finally start tackling the main topic of the video. So, Childe goes to the Abyss, spends 3 months there, and when he gets back, only 3 days had passed on Teyvat. From our understanding of the twin paradox, the accelerating frame will experience less time than the inertial frame. This means that the Abyss must be truly stationary while Teyvat has to be accelerating towards the Abyss. The reason why is because the time of an inertial reference frame appears to speed up when accelerating towards it, as we showed earlier. However, this presents a problem. If Teyvat is constantly accelerating towards the Abyss, wouldn't that mean Teyvat would, crash into it? As it turns out, there are 2 possible solutions to this. The first option is more complicated and involves general relativity. It's possible for an object to be completely stationary in space, but will still be accelerating. As I showed in the previous video, a stationary object at a certain distance from a given mass can experience gravitational time dilation without moving. However, this would require the assumption that Teyvat and the Abyss are within proximity to a third object with a strong enough gravitational field, where Teyvat is much closer to it than the Abyss. I'm not really a lore person, but I don't think that this is the case. The second option is where Teyvat orbits in circular motion around the Abyss, which is stationary at the center. I plan to cover the topic of uniform circular motion in more detail for another video about the drifting physics of the Flame Strider. Hey look, another video to look forward to, so be sure to subscribe so that you don't miss out on it. For the meantime, know that in order for objects to be moving in a circle at constant speed, it needs to be accelerating towards the center of the circle. Even though the acceleration points inwards, it's possible for the object to only circle around the center and never crash into it. This satisfies our criteria, and personally, I feel this is more plausible, so I'll be going with this model, but again, if any lore enthusiasts would like to correct me, feel free to leave a comment and I'll be sure to make another video about it. Typically, to describe an object's position, we use Cartesian coordinates, which are represented by this position vector, x mu. Recall the equation for the spacetime interval in Cartesian coordinates is ds squared is equal to c squared dt squared minus dx squared minus dy squared minus dz squared. Since I'm assuming Teyvat orbits the Abyss in circular motion, it would be much easier to calculate things if we considered cylindrical coordinates. With Cartesian coordinates, you specify 3 perpendicular distances to indicate a position. However, for cylindrical coordinates, you indicate a radial distance from the origin, an angle, and a height above the origin. Whenever you have a change in coordinates, this also will change our spacetime interval. So to get its new form, we just need to recall some basic trigonometry. Basically, if you want to know the x and y position of a point that's at an angle theta, counterclockwise to the positive x-axis, on a circle with radius r, it is given by the cosine and sine functions respectively. As for the time and z positions, they will remain the same. We can substitute these expressions for x and y and use a bit of algebra. After recognizing the most famous trigonometric identity, we're able to get this expression for the spacetime interval in cylindrical coordinates. ds squared is equal to c squared dt squared minus dr squared minus r squared d theta squared minus dz squared. Now that we have the spacetime interval, we can use it to calculate the proper time of Teyvat from the perspective of the abyss. The abyss sees that Teyvat orbits around it at constant radius and angular velocity r and omega respectively. We can also say that the height difference between the two is negligible and that there isn't any change. This means that d theta is equal to omega times dta, dr is equal to 0, and dz is equal to 0. Substituting these into our equation allows us to compute the proper time of Teyvat from the abyss. Lastly, because the abyss is inertial, Ta is equal to tau a. As we can see here, Teyvat's time flows slower than the abyss since the square root term is less than 1. Just to be sure though, let's check from Teyvat's point of view, time for the abyss flows faster. First, we need to make use of a coordinate transform to go to the perspective of Teyvat. What we have to do is to set up a bunch of relationships. First is that the time of Teyvat is equal to the time of the abyss. Second is that the radial distance measured for both Teyvat and the abyss are equal. Third is that theta of Teyvat is equal to theta of the abyss minus omega times t of Teyvat. We have this minus omega t of t because we already know that Teyvat is spinning around the abyss. So if we want to see things from Teyvat's point of view, we need to essentially cancel out any angular change. Lastly, we have that z of Teyvat is equal to z of the abyss. From here, we can actually take the differentials of all of them and express everything in terms of Teyvat's coordinates. We can substitute these values into the spacetime interval, and then after doing a bit of algebra, we can finally obtain the spacetime metric from Teyvat's point of view. We can now use this metric to determine the proper time of the abyss from Teyvat's point of view. Since the abyss is at the center of rotation, we know that r of t is equal to 0, and we also know that its angle doesn't change, so d theta t is equal to 0. It also maintains a constant elevation and distance from the center, so dzt is equal to 0 and drt equals to 0. Right now, it looks as if time passes at the same rate in the abyss from the perspective of someone on Teyvat. However, you have to remember that we need to use the proper time of Teyvat. Earlier, I mentioned that dta is equal to d tau a. This is because the abyss is inertial. However, for non-inertial reference frames, this isn't true, and thus, dt of Teyvat does not equal to d tau of Teyvat. The reason why is because Teyvat's velocity is constantly changing, and we already know that two objects with different velocities experience time differently. To obtain the proper time of Teyvat, we need to make use of its space-time interval. On Teyvat, its change in elevation is 0, so dzt is equal to 0. It maintains a constant radius from its center of rotation, drt is equal to 0, and it doesn't perceive itself to be rotating, so d theta t is equal to 0. From here, we can obtain the proper time of Teyvat. D time of t is equal to d tau of t divided by the square root of 1 minus beta theta squared. Now we can substitute this back into the expression from earlier and get the equation for the proper time of the abyss from Teyvat's frame. D tau a is equal to d tau t divided by the square root of 1 minus beta theta squared. If we compare this with the proper time equation we got from the abyss metric, it can be seen that the two are the exact same equation and are in perfect agreement. The abyss will see time pass more quickly on Teyvat, and Teyvat will see time pass more slowly in the abyss. Just a quick side note, I would like to thank an old friend from the channel, Quantum Thunder, for helping me out with this derivation. Despite lots of research, I actually got stuck while writing the script because I couldn't figure out how to do it. It was not until I reached out and asked him did things become much more clear. So again, thank you very much, Quantum Thunder. Let's get back to the video. With everything that we've established, we can now figure out the conditions needed for Tartaglia's experience to be true. We can take the equation relating the proper time of Teyvat and the abyss, do a bit of algebra, and solve for beta theta. For simplicity, I'll be assuming that 3 months is equivalent to 90 days. Here we can see that Teyvat must orbit the abyss with a speed of 99.944% the speed of light, which is 299,625, 860.3 meters per second. There's just one last detail to explain. How does Childe travel from Teyvat to the abyss? In his story, it's mentioned that he falls through a crack and ends up in the abyss. This sounds like teleportation, but in relativity, that is not allowed because nothing can travel faster than light. However, this does sound like an Einstein-Rosen bridge, or more commonly referred to as a wormhole. Essentially, space could be curved in such a way that two different points in space are directly connected. I currently don't know much about the physics of wormholes, so I can't really go into more details than that. In any case, Tartaglia falls into a wormhole that directly connects Teyvat and the abyss. Let's now put everything together to construct a full explanation for Childe's experience. When Tartaglia was 14 years old, he fell into a wormhole that connected Teyvat and the abyss. Inside, he meets Skirk and trains with her. From his perspective, it appears as if Teyvat is circling the abyss at 99.944% the speed of light. Because of this, Childe sees that the time of Teyvat appears to flow slower than in the abyss. After 3 months, Childe goes through another wormhole that brings him back to Teyvat and finds that only 3 days had passed. From the perspective of someone on Teyvat, that person looking out towards the abyss sees it stationary about the center of its orbit. Because Teyvat is accelerating towards the abyss, time in the abyss will actually appear to be passing faster. And there we have it, a full explanation using real physics from Einstein's relativity. Well, kind of. For the wormhole, it's questionable if they could really exist, as they appear to be unstable and require enormous amounts of energy to keep open. Other than that, everything is plausible. To recap, I did a quick review of the basics of special relativity, explained the twin paradox, non-inertial reference frames, the relativistic Doppler effect, and proper time in accelerating frames, and determined the conditions necessary for Childe's experience to actually occur. Don't forget to like and share the video if you enjoyed. I cover math, physics, and engineering related topics, and in fact, one of the ideas I have in mind is to calculate the total force Mavwika experiences as she drifts on her flame strider. I also plan on explaining Genshin's gravity based on the calculations I presented in this video. Both of these will obviously be on my next video topic poll, and if you don't want to miss out on those, be sure to subscribe. Once again, a very big thanks to my very first channel member, Eternal Dango Work. I actually got to see some scrap parts of the script, one of which was a derivation of the Minkowski metric in cylindrical coordinates using the Jacobian. If you want to see that in addition to other behind the scenes stuff that I've uploaded, consider becoming a channel member. Lastly, let me know what you guys think by leaving a comment or even a super thanks. If you have any questions, don't hesitate to ask. Relativity is not an easy topic, so don't feel discouraged if there's something you don't understand. To any lore enthusiasts among the audience, I would like to hear what you think about my proposed model for the Abyss and Teyvat. Of course, if I got any details wrong, let me know in the comments below. A lot of you in my previous video definitely told me about how it's possible for an Earth to exist in the universe that Teyvat exists in, but whatever. It's actually pretty ironic that I said that as a way to say the video was not going to be lore accurate. As you might know, these videos take a lot of time and effort to make, so any support that you can give to help boost me in the algorithm would be greatly appreciated, as I really can't do it without you guys. And I'm forever grateful that you guys are willing to watch this stuff. So yeah, thanks for watching and hope you've enjoyed.